Okay, so let's talk about Cartesian products. We'll start with a definition, but we're going to need to define the notion of ordered pairs. So we're going to define what an ordered pair is. Now let A and B be objects, any kind of objects that is well defined. We define the ordered pair A and B to be equal to the set of objects containing the singleton. So since we have only one element, we call this a singleton. And another set containing the two objects A and B. I'm defining this just so you have an idea of how we define the ordered pairs. But what I really want you to understand is that this here leads to the definition for equality. Using the equality of sets, we can have this little fact here. So A is equal to A prime B prime. If and only if, so we have our biconditional. We have an implication in both directions. I'm going to explain that in a little bit. So they are equal if and only if A is equal to A prime and B is equal to B prime. Okay, so what this means is that if I state that those two pairs are equal, well, necessarily I have that the two corresponding coordinates are equal as well. And if I start from the other side, if I state that I have this equality right here, then the pair that is formed using those objects are equal as well. Okay, so it goes both ways. What's mostly important is that you remember this notion of equality. The definition is just an, oh, by the way, we can define ordered pairs using sets. The actual definition that we want to talk about is the Cartesian product. So we're going to need two sets. So let S and T be sets. Now we define the Cartesian product. So cart product S cross T to be the set. So our Cartesian product is a set of all ordered pairs S and T, where S, our lowercase s, is an element of our set S, and our lowercase t is an element of our set T. The notion of an ordered pair means that the order in which we consider our Cartesian product right here is important. S, the product of S and T, is not equal in general to the product of T and S. If S is equal to T, well, certainly they're going to be equal. Okay, so in our first example, we're going to consider the case where we have one of our sets to be empty. Okay, so one of our sets is empty. Let S be a set, the empty set with S. Well, I can't even form a pair, because you can't even form a pair A and B where A is an element of the empty set and B is an element of S, okay? That right there does not exist. It does not exist. So this is why we're going to consider both cases, okay, so when the empty set is on the left or the right, in both cases, it is the empty set because we're not able to form an ordered pair. Even in our definition, we start with two objects. Now for our second example, let's see or talk about, we have the set 1 and 2 cross the set 1, 2, and 3. So what are the objects? What are the pairs of this set right here? I should start with 1 and 1. So 1 and 2, 1 and 3. Then we also have 2 and 1, 2 and 2, and 2 and 3. Okay, and this right here should convince you that the order in which you place the two sets is very important. If not, try to come up with all of the objects of the set 1, 2, 3 cross 1 and 2, and do that, and you'll be able to see that you have different pairs. Using Cartesian products, we can define the set of coordinates. The set of coordinates of the Euclidean plane. What that is, simply, is the cross product of a set of real numbers with another set of real numbers. In this case, when we deal with two of the same set, we often use the notation squared, like this. So if I have, a cross product of three sets like this, well, I can write it as R3, and so on. This notation is going to be more or less consistent. Sometimes we'll opt for using the cross symbol or the exponent. We're going to be more or less consistent about this. So this is formed of all the pairs x and y, such that x and y are both real numbers. Now, I say the set of coordinates of the Euclidean plane and not the Euclidean plane itself, because when we're talking about the Euclidean plane, you need a metric, you need a notion of distance, which we're not defining yet. It's a subtle distinction, but a very important one. What else can we talk about? Now, having defined Cartesian products, it's very easy to define a circle. So a circle is defined by the set of pairs x and y, such that we have x squared plus y squared is equal to, okay, so if our circle is of radius r, where r is a positive real number, remember, we can write this as r plus and the asterisk. So this would be our circle. If we define a disk, we could use the set of all pairs x and y such that x squared plus y squared is equal or smaller than r squared. Now we would need to define this. So this needs to be defined. But, I think you've encountered inequalities before in your life, so I'll allow myself to talk about it. The disk here would correspond to, since we have an inequality, it corresponds to the entire, this would look like all of the set of coordinates in the circle and in the disk, if this would be our geometric representation of our set of coordinates. Okay, so let's go over an overview of what we've seen. We started with the definition of an ordered pair. So we have two objects A and B, and we define an ordered pair to be of the set containing the singleton A and another set containing A and B. Okay, so this definition corresponds to this notion of equality using equality of sets, but you can just take this for granted. You're not really doing any harm to yourself if you're doing that. We were then able to define the Cartesian product. So we have two sets S and T. We define the Cartesian product S cross T to be the set of all ordered pairs S and T, where our first coordinate is an element of S, our second coordinate is an element of T.